Hello everyone. Today we are going to understand what is the effect of the cross section on the beam if we apply a same type of load on three types of beam. Only there is a difference of the cross sections. Okay, so we will decide it on the basis of the bending stress generated and the maximum deflection generated. Okay, so now, not taking too much time, we are going to start with the problem that we have. We have a beam, simply supported beam, in which left side support is a hinge support and right side is the roller support. Okay, the beam is of length of 4 meter, and there is a center load of a point at C, which is of how much it is? It is of, you can see, it is of 5000 newton, and then there is a UDL of 2000 newton, and the UDL is applied on throughout the length of the beam, that is 4 meter. The material is of beam is 210 gigapascal of Young's modulus. Poisson's ratio is 0.33, and Young's model yield stress is yield strength is 250 megapascal. So but this 250 megapascal, the yield strength is not going to be uh, used, because this particular loading is only to be applied, and this analysis is completely based upon the elastic deformation. We are not going to do some plastic deformation into the beam. Okay, so for that we have a basic knowledge of how to find out the maximum bending stress or maximum bending moment, or and the maximum deflection. In this case, there is a point load, and this is also the UDL is throughout the length, and the point load is at the center. So we can easily find out the deflection, and which using analytical method. You can see in the upcoming content. So the cross section is like, the cross section is the box section, pipe section, and eye section. You can see that there is a 200 of all the dimensions. Actually, all the dimensions are in mm. Okay, all the dimensions are in mm. Now I'm going to see that what is the effect of these cross section if I use the same length of beam, use the same kind of supports, use the same kind of the loading conditions. So what is the change in the bending stress generated and the deflection generated at the center because of changing the cross section of the beam? Okay, so we have to make three setups for three cross sections. Okay, bending stress, you can find out very easily that how to find out the bending moment. You can understand it from the how to draw the BMD, bending moment diagram, and or you can apply some sign conventions and equilibrium equations to find out this bending moment. What is why is the distance from the neutral fiber to the other fiber on which you are going to find out the bending stress. But in this case, we have to find out the maximum bending stress, so we have to keep this maximum. Okay, and we are going to understand that where is the maximum bending moment. So maximum bending moment in this case is at the center. Okay, is at the center, and what is I? This is the moment of inertia, and y max is the 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 half of the cross height, half of the height, because all the three sections are symmetrical through y axis. So y max is, for this is 100, for this also 100, and for this also 100. Okay, for this also 100. So y max, you have to remember that it will be 100 that means 0.1 meter. Okay, the next is the deflection in the beam. Deflection in the beam is equals to the total deflection because of UDL plus total deflection because of point load, and that will be the total deflection of the beam at the center. The maximum deflection will be at the center. Obviously, we can see that the loading is also the symmetrical, so we can say that the maximum deflection will be at the center, that is point C. Okay, now these are the mostly the objective of the this particular beam analysis, and we are not going to be theory because we have already understand in the previous semesters also. So these are the cross sections. Okay, the materials I have already discussed that Young's modulus will be 200 gigapascal and Poisson's risk will be 0.3. And then the boundary condition, which is very important. As you can see that there is a hinge support at the left side and a roller support at the right side. Okay, so this is x, this is y, and this is z. So I'm not going to use z because I'm going to make the beam in the 2D plane, so it will not be used. That means z. X ko we will say that x is 1 first direction and y is to be set to be second direction. Okay, x is 1, y is 2, and z is 3 actually, but z is not going to be used here. So at the hinge support, what is u? U is the deflection. U is the deflection. Okay, what is at the hinge support at the left side? Left side, u1 and u2 will be 0 because this beam is not going to be move in the x direction and also in the y direction. Okay, but deflection, the angular deflection will not be equals to 0 because in the hinge support the beam will deflect like this. So it means the beam was initially here, so there is angular deflection, you can see that. Okay, so the angular deflection, that is r means rotational, so this is not going to be 0. Okay, and at roller support, as you can see that this roller is here, so there is a tendency of motion of this beam in left and right direction. Okay, left and right direction means x means 1, so in the x direction there will be some tendency of motion, so u1 is not going to be 0. U1 is not going to be 0, but rotational angular displacement will be, sorry, it will also not be equals to 0, and but u2 is equals to 0 because beam is not going to be going to move in the upward direction or downward direction. Okay, so these are the boundary conditions that we are going to be used in this particular software. Okay, so these are the boundary conditions. We will see the results later on, analytical results as well as the computational results. So this is the interface of the Abaqus. We are I'm going to take start with the module, that is part. What is part? Part means part we are going to draw the drawing for the beam. So clicking on the part, then create part. So I'm going to give it name beam. So there is no use of z direction plane, so I'm going to use it 2D planar, deformable, and wire type. And you can see that the maximum dimensions of the beam is 4 meter, so I'm going to use here the 6 meter workspace. Okay, little bit larger than the object. Now I'm going to take line command to create the line or the length of the beam. The first coordinate is 0, 0 because we are using x and x, y only, so 0, 0. Then second point is at how much it is, 4 meter, 4, 0, enter. So now we can see that this is the length of the beam. I'm going to make it done. So this is the length of the beam. Okay, we have drawn the axis of the beam. Okay, now going to the next part, that is property. We are going to give the property of the material, but material is steel. Young's modulus is 210 gigapascal, so I'm going to write it steel material. Then we have only to specify the mechanical property. In the mechanical also the elastic property, and then elastic the Young's modulus must be provided, so it is 210, And what is gigapascal? Gigapascal is the 10 raised to the power 9. So here in the abacus we only need to write E9. E9 means 10 raised to the power 9. Poisson's ratio is 0.3. Then okay. So material has been saved. Okay. Now I'm going to make the three profiles of beam. Profiles means the cross sections. Okay, I'm clicking on this particular section, this module, that is in the property module, uh, create profile. Create profile. The first one is the box type, rectangular. Hollow rectangular means box type. So I'm going to write it box profile. Box profile, and then continue. So you can see that the various dimensions is being asked here. So what is the width? Width is 100 mm, that means 0.1 meter. Height is 200 mm, that is 0.2 meter. And thickness is throughout the uh, perimeter, you can say perimeter, throughout the length, throughout the perimeter, the thickness is constant, and that is 20 mm. That means 20 mm, that is, no, it was not 20 mm. Let's see that what is the thickness. Thickness is, sorry, exactly it is 20 mm. That means 0.02 meter. Okay, 20 mm means 2 centimeter. 2 centimeter means 0.02 meter. Then okay. Now I'm going to create one more profile, that is pipe type. Okay, pipe type, pipe profile, pipe profile, then continue. What is the outer radius of the circle is 0.100 mm, that means 0.1, and thickness is same, that is 0.02 meter. Then okay. The next profile was eye type, eye profile. Okay, eye profile. What is the dimensions? The first dimension is L. L is the centroid distance from the bottom. Centroid distance is half of the total height, that is 100 mm, 0.1 meter, zero point 0.1 meter, and the total height is 200 mm, that means 0.2 meter. Width is 100, so 0.1. Second width is also 0.1. Thickness everywhere is same as 0.02, 0.02, and then 0.02. Then okay. Okay, next is we are going to create the section. Means we have created the profiles, but we don't give the instruction to the abacus that that profile is lie with the this axis. Okay, so I'm going to create the sections. Create the section. Section is, first is section is box section. Okay, box section, I'm creating that box section. Okay, and this is a beam type. So beam type, beam, and beam here also. Then continue. Box section here, the which we need to profile. We are going to give this profile to the section, that is box section, box profile, meshed. And this is the steel material. We have created only one material, and then okay, simple. And then again create the section. Second is the pipe section, pipe section, and then beam, then continue, and then here the pipe profile, and then okay. Next section creating, and then it is a eye section, eye section, beam, beam, continue, and here the eye profile, and then okay. Then next is the section assignment. We have created the cross section, we have created the material also. So we have to provide connectivity in between the material property and geometrical property. So we have to assign the section. That means this section is related to this particular material. Okay, so assign the section. I am going to select which axis is connected with that particular profile, and that axis is going to be connected with the which material. So I'm going to tell the abacus that material and that cross section is related to this particular axis. I'm not going to create any set. Set means some set of operations we are going to create. No, we are not going to create any set here. I'm going to select this axis and then done. You can see, sorry, I'm going to analyze the box type section first. Then after we will come back here and then assign the section to the pipe, and then again come to back to this section, and we will assign to the I section to analyze the whole thing. Okay, so I'm going to select only box section here. Okay, assigning the box section to this particular axis. Okay, so we will do the analysis firstly on the box type. Okay, and then the last one is create the vector for the cross sections. So I'm going to just clicking on that and then done. Sorry, select the region to be assigned a beam section orientation. I'm going to select this beam, then done, then okay. We have to do okay and okay, and then done. Okay, so we have created the beam orientation also. This is the characteristic of the beam kind of problems, and then we can directly go to the assembly. As you can see that there is only one part, so we don't require to do assembly, but in abacus it is the sequence to do some other analysis. So we have to tell the abacus that there is only one part, so we have to go to the assembly first and then create the instance. That instance will tell the abacus that there is only one part. We are not going to interact with any other parts. Okay, so creating the part beam has been selected, that beam which we have created in the parts module. And then dependent, we can do that dependent or independent. Independent means if we take an example of a table and there is a 4 legs and we need to do the meshing means creating the elements in a different legs. The number of elements are different in all the legs, so we have to make it independent. But here we have only one part, so it is not going to change anything. But by default it is dependent, so I'm keeping it by default. Okay, then okay. So the next thing is we are going to create step. We are going to create a step is here. Okay, before that I want to make a reference point so that I'm going to create a reference point at the center from the tool here also, and I'm going to click here on a reference point, and then assembly I have already done. Now I'm going to create step. Okay, what is the step is step is very simple here but very important. Okay, so creating a step is bending. I'm writing here the name of the step. It is not initial is by default. We have already done initial steps, and now this is the second step, that is known as bending. Okay, so here static general, keep it simple, that is general, static general, and then continue. Okay, here also okay, step has been created. Next is interaction, load, mesh. Okay, so I'm going to first to do, there is no interaction because there is no environmental property is going to change the property of the beam, so I'm not going to uh, use this interaction module. So I'm going to directly to the mesh. Okay, the mesh. In the mesh we need to create seeding. So where we are going to create the elements, we have to decide it from the seed. Okay, So it is coming as an error that dependent part instance cannot be edited or assigned mesh attributes. So I'm going to change it part. We have created the part, so we haven't done any assembly, so we are going to do the meshing on the part. Okay, so part is beam. Now seed part. So seed part, I'm going to uh, create a size of elements. I'm going to keep it 0.001, 0.001. Then I'm going to apply it. 0.001 means 1 mm. The size of each element is a square, and the shape is a square, and the size is 1 mm. So you can see that there is seeding has been done. I'm going to mesh the part, then okay. So you can see that the 4000 elements have been generated on the part. 4000 elements is very much large for this particular 4 meter beam. So I'm going to make it a small, the larger elements more than this 1 mm. So I'm going to take it again. The size is 0.005. The 5 times I'm increasing the size of the element. Okay, apply, delete the previous mesh, then apply, then okay, then mesh the part from here, then yes. Okay, you can see the 800 elements have been generated on the part. Only 800 elements, that is sufficient for us. Okay, now I'm going to make a center point on which we are going to apply the point load. So you can see that here, center point. So Abaqus cannot identify the center point until unless we have specified it. So I'm going to make a set point here. Okay, from the tool, make sure that we are in the mesh module. Okay, then tool, set, create set. So what is the name of the set? It is the point load set, on which we are going to apply the concentrated centered force. Then node, continue. Select the node for the set. Node is at the center, but I'm not identified it. So we have to create the reference point first. Reference point from in the part. I have created the reference point in the assembly, which is not visible here because assembly has not been done. Okay, so I have to create the reference point in the part module. So I'm switching it to the part module, and then tools, and then reference point at the center. Okay, the reference point has been generated. Now I'm going to the mesh, and mesh has been done, and you can see that reference point is being shown. Okay, here it is part. Okay, then tool, then set, create, and what is the name of the set? PL underscore set. You have to remember this name because you are going to use that particular set. Then node, then continue. I'm going to make the set point over here at the center. That's okay. Then done. Okay, now I can go for the load. In the load, we can apply the forces and you can apply the boundary conditions. Okay, so I'm going to apply the force first, create load. So first load is the point load. I'm writing it PL, and then mechanical, and then concentrated force. Remember that the load must be made in the bending step. Okay, bending step, and then mechanical, that is concentrated force, and then continue. It is asking select the point for the load. I am going to apply the load on the set. You can see in the right bottom corner that sets, where the sets we have created the beam point load set, and then continue. It is asking for the magnitude. CF2 means in the y direction. in the y direction, but y direction upward is the positive, so the force is in the downward direction, so minus of 5000 we have to apply it at the set point, that is at the reference point. Then okay, you can see the point load has been applied here. Okay, the next step is apply the UDL. So I'm writing it name UDL, bending concentrated force. This is not a concentrated force, this is a UDL. UDL means at the on a line. So find out where is the line load. Line load is here. Okay, then continue. Select the body on which we are going to apply the point line load, this UDL, throughout the length. Then done. What is the magnitude in the y direction? It is minus of 2000 Newton per meter. Then okay, you can see the UDL has been applied. Okay, so load has been applied. Now we are going to create the supports by applying boundary condition. Create boundary conditions. So remember this, the boundary condition must be applied in the initial step. Okay, in the initial step. So then in the initial step, then mechanical, then I'm going to apply the displacement and rotation kind of boundary condition to define the supports. Okay, displacement and rotation, mechanical, displacement and rotation, then continue. It is asking select the region for the boundary condition. The first region is the left side. Okay, first of all I have to give the name of the support, the boundary condition first, that is the left support. Initial, mechanical, displacement and rotation. Continue. I'm going to select the left point on which I'm going to apply the boundary condition. Then done. So we have defined earlier that what is the displacement kind of boundary condition here at the left corner. U1, U2 must be 0. And in the abacus, if we tick down like this, it means 0. Okay, so tick means 0. So I have to tick on the U1 and U2, but the rotation will be there. The rotation UR3 means with respect to Z axis there will be some rotation. Okay, angular deflection. So U1 and U2 must be 0 at the left point. Then okay, then again we are going to create the boundary condition at the right side. So right support, mechanical, displacement, rotation. I'm going to select the right support and then done. And right side is the roller support, right? In the right side there is a roller support, so the beam is having the tendency of moving in the left and right, means x axis. In the x axis the displacement is not equals to 0. Okay, so here only U2 is 0 and then okay. So we have done with the boundary condition also. Now we can go for the job. So job means we have defined all the things. The first job is for the first box type section. Okay, so job, create job, and this is a box type, so I'm writing it box job. You can write it the name of your name, so that you can find out easily that this work is yours. Okay, you can type your name, whatever the name is here, it will be shown in the result window. Okay, then continue, then okay, then go to the job manager, then submit your job, that is box job. Submit this job. Okay, it has been submitted, but it will take time to run. So it has been submitted. Running status, you can see completed successfully. You can see this message here, and the completed will be seen here also. Successfully completed, successfully, this is also completed. That means you can see the results. Okay, where is the result is here, result. So in the result, this is the visualization module. Here it was the job module, and then you can go for the visualization module, in which you can see the results. Okay, so where is the job is the box job. You can see the name of the job, box job. Okay, then you can go for the deformed contour type shape. Plot the contour means uh, different colors will show the different types of output values. Okay, so the I'm going to click on here. As you can see that this is not a beam, this is a axis of the beam. Okay, it has been deflected like this. Okay, and this is uh, the values of the stresses. The S means stress. If you want to find out the deflection, you have to select it here from here, that U. So you can see that it is 1.42 into 10 raised to the power minus 3. Means if we multiply with the 1000, that means 1.42 mm deflection at the center has been generated. Okay, what is the stress value? Bending stress value, it is 1.784 into 10 to the power 7. That means 17.84 in megapascal at the center. Bending stress has been generated. Okay, so now I'm going to see the beam kind of profile. Okay, beam kind of profile. So you have to go to the view at the top ribbon, view, ODB display options. Here the render beam profile, I'm going to apply it, and then okay, you can see the height of the beam. Okay, if you want to see all the way, you can use this rotate view. I'm going to rotating it by clicking long, pressing the left click, and you can see the cross section. This is a box type cross section. Okay, this is a box type cross section. Okay, you can see the axis also in the center. Next is, if you want to, you need to use the isometric view. Okay, you have to apply the isometric view to see uh, all the three dimensions of the beam. Okay, so now we are going to make the same analysis for the next section, that is pipe section. Okay, so I'm going to directly to the pipe. Acha. Okay, so you can find out the values of the stresses and the deflection from here, switching on U and S for stress. Okay, this is the name of the job. The name of the job will be shown here. Next is going to the property module, because section was there. Assigning the section, I'm going to assign the section again to the same axis with a different profile. I section, no, pipe section first, then okay. So now we have to go to the job again, and then create the job. And this is a job 2. I'm giving it name, that is pipe job, and then continue. Okay, job manager, this is the pipe job, you have to submit it. This was completed, this has to be submitted. Submitted. It will not take too much time, because mostly the things has been compiled in the previous job. Completed successfully, then we will have results. successfully. Okay, result. You can see the pipe section here, deformed kind of, and isometric. This image is required. Okay, this image is required. Now you can see the stress 1.76 into 10 to the power 7, and deflection is 1.405 into 10 to the power minus 3. Okay, the last one is I section, assigning the section to the our beam, and then done. What is the section? I section. Then okay, go to the job again and create third job. Job 3, that is I job. Continue. Okay, job manager, submit it. Completed. Okay, you can see the results. This is the I section, deformed, isometric. You can see this I section clearly. And what is the stress generated here? It is 2.08 into 10 to the power 7, and it is also at the center of the beam and at the bottom of the beam, or you can say top of the beam, the maximum bending stress generated. Okay, what is U here? U is 1.66 into 10 to the power minus 3 meter. Everything, all the uh, units are in MKS, right? All the units are in MKS. Now I'm going to bring all the analysis, means all the job at the single window to take the screenshot. You can take the screenshot to make the reports. Okay, so I'm going to use viewport. Viewport, you can see create some what we can say, uh, create some viewports for the three different jobs. Okay, two window has been created. One was earlier, it was earlier, and then this is once again. I'm going to create one more viewport. Okay, so we have three viewports, but we cannot see all the three all together on the screen. So I'm going to make it tile horizontally, because you can see this view is also need some horizontal space. Okay, so I'm going to use tile all the three screens on a single page, tile horizontally. But we need to see that, we can see that the beams are getting shown very small and small. Okay, so we have to make it larger using tiles vertically. Okay, so this is the image that we can see with the stresses, but in all the three viewports only the I sections are being shown. Okay, so I'm going to click it one by one. This is the first one, so I'm going to change this from here, box and deformed. Select it here. This is pipe and deformed. Okay, and isometric also. And here select I was already, and deformed is also already there. Okay, so you can take the screenshot of this page, and the similar way, in the similar way, you can go for the U also. This is for the stresses, and if you switch here from the U means deflection, you can show. Okay, so this is all about the beam analysis, in which you can compare about the stresses as well as deflection. In this particular case, you can see the maximum stress generated in which cross section, in the I section. So bending stress generated in the I section is higher than all other cross sections, and deflection you can see in the um, I section is also greater than others. I'm going to check it out. U, U, and this is U. The maximum deflection is also in the I section. You can see 1.6, and here it is 1.40, and here it is 1.42. Okay, so this is all about the beam. You can find out all the three values using analytical method and compare it with the computational method, that which method is better for the analysis. Okay, thank you all. Thank you everyone.